Hello guys, welcome back. This is our first video on refrigeration cycles. The objectives of this video will be introduce the concept of refrigerators and heat pumps and how do we measure performance. Of course, we are going to analyze the ideal and the actual paper compression cycle for refrigeration, which is the most used cycle. We started using in around 1924. And basically we are using the same machinery. We're not going to review the factors involved in selecting the right refrigerant. I will leave an article on that. But we are going to discuss the operation of refrigeration and heat pump systems. Some evaluation of the performance of an innovative vapor compression refrigerant system, and we're going to skip the gas refrigeration and absorption refrigeration system, since the covering that we have is very basic. We're going to use part of what we have in the book and some other ideas. Okay, so let's start just by remembering our Carnot cycle. And you remember that this Carnot cycle, we started with isentropic compression, and then we have isothermal Q addition, then we have isentropic expansion, and then we have our isothermal heat rejection. What we said is that all of these processes were reversible, and this was the model for thermal machine, right? I mean, from this machine we have high temperature reservoir that will provide heat to a heat engine that will produce some work. Because of second law, we're going to reject some heat to a low temperature reservoir. So all of these components are reversible: the isentropic compression, the isothermal heat addition, the isentropic expansion, and the isothermal heat rejection. So what we can do is we can revert, and please note that we have here similar, we have a rock, and it will naturally flow from high to low. So this heat can be represented as this rock. Naturally will flow from the high temperature reservoir to the low temperature reservoir, right? The only way, let me change this just color, so we can differentiate. Let's use a green, hope it looks better. The only way we can move this rock to the top is by adding some work, right? We need to put it into a truck, or we need to put into maybe a pulley and a motor. So there's no way that the rope will flow from low to high without adding some work. Same could be done for thermal systems. So we have the high temperature reservoir, have the same low temperature reservoir. Let me change this one. This is low temperature. We will have our machine here, and in order to have this heat going the other direction, instead of extracting work from the system, we will need to add some work. This is similar to adding work to this pump, to this rock. So why do we start with the Carnot cycle? Because as we said, all of these components are reversible. That means that we can go back to the state, to original state, without leaving any trace in the universe. More important than that is that we can reverse it. I mean, we can work the operation in the other way. So I'm going to draw exactly the same. This is a turbine. This is my compressor, heat exchanger, heat exchanger. So now, if instead of connecting it this way, I make it operate in a reverse manner, it is in this direction, heat will go the other way too, right? We're gonna add some heat, then we are gonna compress it, we're gonna reject some heat, and then we're gonna expand it. So this is what we call the reverse Carnot refrigeration cycle. Okay, similar to our Carnot, we said that the efficiency here was QL in work divided by Q in, what I need to provide. And because I thought this was isentropic, I could put it this way after manipulating. Right. Okay, we can do the same with the Carnot cycle, and we can say that what I want, here's the cooling effect. So what I want is QL. What I need to provide is work in, and I will not call this efficiency, I will call it COP, coefficient of performance. If I manipulate similar to what I did with these temperatures and entropies, COP will be TL divided by TH minus TL. And I will add here an R, meaning that this is a refrigerator, because what I like is to cool down something, and that's the effect that I want in a refrigerator. But I can also define for a heat pump where what I am interested in is in the heat that I have here. So COP will be now TH divided by TH minus TL, and this will be for a heat pump. Notice that this is similar to this. If it's not apparent to you, remember that this is TH minus TL divided by TH. So you can say it's the opposite. Okay, so this will be the best Carnot refrigeration, the best refrigerator we can get. Let me just make sure that we clear this is Carnot COP. This is the best that we can get, but we can never get it. So the same problems that we have with the Rankine cycle, in which we would like to have our if I draw my TS diagram for a substance, let's say this substance could be water or any other substance, and I try to accommodate a Carnot refrigeration cycle here, we remember that we can do it with change phase. So we will have something like this. We have two isentropic processes, and two isothermal process with the phase change. We notice that we have the same problem, so two-phase compression and two-phase expansion. So what we're going to do is we're going to modify it a little bit. We're going to introduce this blue one, and we're going to extend it until the point we get saturation, right? So we know that we can extend this line here. This will be my saturation line, and then I will have my isentropic compression. I will do the same here. I will try to accommodate until we get saturation. And this is almost our TS diagram for refrigeration. One problem we have though is that in this part, this is a turbine. It should deliver some work, and it's difficult for us to build such a small turbine. It's not practical, so what we do is we use an expansion device that will change our cycle. And with expansion device, when we discuss entropy, we said that expansion is one of the ways of one process that is very irreversible, so the entropy will increase this way. So if I erase what I don't need, and let me see if I don't erase something that I need. I will erase this because I will not produce work. I don't have to go to the end, to the saturation point. I'm not expanding isothermally, isentropically. I am expanding with some entropy generation, and we just need to complete this. So this will be my cycle, and I erase this part. So this will be my vapor compression cycle. I will start with saturated vapor at the exit evaporator. It will compress until a certain pressure. Then we reject heat as in a condenser, change phase until we get to this point where it's saturated liquid, and then we expand, and we have a mixture of liquid and vapor, and we introduce into the evaporator, and it will evaporate until it has again saturated vapor. Before we move, and we are going to have another video for that, I will try to keep this video as short as possible. Just recall what we discussed in class, that in order to understand refrigeration, all that you need to know is about beans. Why? Pressure will change the temperature at which a fluid, and this fluid could be water, alcohol, or some other fluid I can call 134A, for instance, will boil. And the second thing that we need to recognize is this word boil. I don't think that this was a good selection. We'll change for this. Boil. Because boiling is change of phase. And can occur at any temperature. For instance, at pressure of 100 kilopascal, 100 kilopascal is atmospheric pressure, a fluid called 134A will boil at minus 26. So temperature and saturation temperature is a function of pressure. So by changing the pressure in the system, we can change the temperature at which it will change phase and at which it will absorb heat. So next video we're going to start. This is what we discussed today is the Carnot refrigeration. Next video we're going to talk about the ideal vapor compression cycle. Thank you. Okay, and just as we mentioned, we have two different apparatus that we can use using the same technology. One will be the refrigerator and one will be the heat pump. They use the same components, and the only difference is in the desired output. In the refrigerator, the objective is to remove heat from cold space. Think of your freezer or your air conditioning at home. So this is the desired output, QL. So in the COP definition, QL will be in the denominator, in the numerator. For a heat pump, which is not very used here in Mexico, but is very used in the US and in Europe, we would like to have the desired output as a QH, the heat that we are rejecting, and we're going to use it to warm up a house, for instance. So since this is the desired output, that will be in the numerator, and the heat we're going to get it from the cold environment. Okay, so next video we're going to talk about vapor compression, the ideal vapor compression. Thanks.